It is 2 hours UTC, and it's time again for Astronomy Daily Live. Hey, everybody. Hope everybody's doing well out there in the world and the universe. Everything's well here. It's a nice, slow, quiet weekend, taking it a little bit easier than normal, just lazing around, not doing much, just sort of being lazy. It's getting pretty warm here. It's we're starting to get into the the warm, supposedly dry season down here in southeastern Arizona. Drier than normal, but we actually had some just hints of sprinkles today. So that's a little unusual, a little strange, but yeah, it's getting pretty warm, but that's pretty normal. So I'm going to tweet. Somehow I'm remembering to tweet. Can't believe it. Write this one down because it doesn't happen very often. There we go. Cool. So hope everybody's doing well. I'm going to pop open my chat here. Make sure that's going. I'm going to make sure that the live stream is actually going. Dun, 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 dun. All these technical things before we actually get started. Hey there, Bobby. Hope everything's well with you. Glad you could stop in for a while. That's one of the cool things about a daily live stream, right? Is that you can come in whenever you want, right? I mean, if you want to come in um, uh, every single day, please do. Please do. You are welcome. Welcome, welcome. If you want to come in every other day, every week, every month, every year, whatever it is, come on in. You are welcome to join the circle of friends who share this common passion for the science of astronomy. Cheers. Yep, all is well here too. I was just saying it's been a nice quiet day. So like to have those from time to time, quieter than normal. I sort of purposely have a pretty quiet life anyway. So, but sometimes they're even more quiet and calm than normal. So yeah, everything's going well. I was looking at the GAIA data release 2 data today, trying to see if I can do some artsy things with it. So you can go over onto my Discord server and see what I've been up to there. It's sort of that the artsy thing sort of followed the Gaia thing, which followed a search for binary stars, which uh, which was caused by uh, the project that I'm doing with this telescope and my CCD camera. Now, this is a Celestron Nexstar 8SE. It's an 8-inch, 0.2 meter telescope, um, Schmidt-Cassegrain telescope. My CCD camera is an SBIG ST7ME. It's an older um, camera, oldie, but I'm thinking still quite nice. But and so what I'm trying to do, I have this big uh, overarching, not exactly a project, but a plan that I would like to um, uh, get started on. But in order to do that, I need to know how well this system works in terms of doing um, 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 astrometry, which is the measurement of the positions of targets, and photometry, which is is the measurement of the brightness of targets. And I'm trying to characterize this system, just see, how good is it? How bad is it? All of that. And the astrometry is pretty easy, right? Because it's just, if you're looking at a star, it's like the star is right there. That's about it. And I can measure the accuracy of that and precision. And those are quite nice. I'm getting sub-pixel accuracy and precision on measuring the positions of targets. Photometry is the thing that sort of is continuing to mess with me. Um, I, I'm seeing accuracies and precisions that I'm not expecting, and maybe my expectations are too high, but it sort of goes beyond that. There's some, yeah. I'm not happy with what I'm seeing, and I'm not exactly sure if it's the software that I'm writing and using to make these measurements, or if it's sort of the data collection technique. I'm just not sure where this problem I'm seeing, which is mainly um, um, inconsistency. It's lack of precision and lack of accuracy. See, what I can do, the idea here, right, is that I should be able to look at a field of stars in this scope, right? Take an image, take a series of images, and then I should be able to measure the magnitude differences between all the stars in the field of view. So I can use like one star as a reference and say, okay, that's whatever it is, and then measure the difference in magnitude of the other stars in the field of view relative to that star. And I can choose my reference star and all that. And then what I can do, once I have that set of measurements, which are differences in magnitudes, right, I can go to a database like GAIA, right? And they have also measured the brightnesses, magnitudes of these stars, and I can calculate what the differences are there, and then I can compare, right? What GAIA says and what my system says. And I'm off quite a bit, and it's not consistently off, in sort of one direction. I'm not off, too bright or too faint or anything. It's all over the place, and so I'm trying to understand exactly why, and I haven't nailed that down yet. So what I have been doing is I've been looking at open clusters. So I've been looking at like M41, M46, M37, M67. Uh, uh, Clusters of stars where there's a lot of stars and a lot of variety in terms of brightnesses. And I thought that would work really, really well, right? But for some reason, it's not. It's not, and I'm not quite sure where it is. I don't think I don't think it's noise in the camera because I can look at the background sky, and the background sky is consistent. It's really, really, you know, nice. I can look at my darks, right? And those are very, very nice. So I don't exactly know uh, um, where exactly the problem is. So I'm not exactly grasping it at straws yet. But one of the things that I do know um, is that because I'm not guiding, I can only take relatively short exposures, you know, like 2 seconds, 3 second exposures. The tracking is okay on those time scales. But if I were to do, you know, like a 10-second exposure or a minute exposure, um, uh, then uh, basically uh, all I would see is just these streaks, right? Because the tracking isn't perfect. If I had a way to guide, then then that then that problem may go away. So because I have to do relatively short exposures, my signal strength, how uh, CCDs take in the light and um, convert that flux to a number, right? And the camera that I have is a 16-bit camera, which means that numbers can go from 0 to 65,535. And so that's the full dynamic range. Well, with a 2-second exposure and about a ninth magnitude star, I'm getting a flux value of about 2,000 or so. So it's pretty low light level. I don't know if that's the problem or not, but the direction that I'm sort of going now is that I need to look at some brighter objects, right? But I need to be able to do this differential magnitude. I cannot measure the actual magnitude. I would have to be able, well, um, I could, but I would also have to measure standard stars um, whose magnitudes are known, and then I would have to, I mean, it's much more complicated. So I wanted to keep this simple, right? I wanted to keep it simple. and uh, and so I'm just looking at the magnitude differences. So in order to do a difference, I need at least 2 stars, right? So it's like, okay. I will look at some bright binary stars that have, relatively decent separations. My pixel scale, um, one pixel on my CCD camera is about one arc second in size, and so I really can't resolve any separation between stars less less than that. I'd much rather do like 30 arc seconds or more. So I've been going through a list of binary stars that, of course, are up at sort of a reasonable time of the night. Make these observations and then look at the differences in brightnesses um, between the components of binary stars. And I want to look at some bright stars, fourth magnitude stars, fifth magnitude stars, sixth magnitude stars, maybe down to eighth or so, right? So I've got a list of candidates, and yeah, I think pretty much the next clear night that I have here. I don't care um, that much about the moon or anything like that. It doesn't matter when you're doing differential um, um, photometry. A lot of things don't matter. Uh, so that's why it's so easy, right? It's supposed to be so easy, but yeah, there's always surprises. There's always things like, oh yeah, I didn't think of that, and so yeah, it's a process, and I'm going to get to the bottom of this one way or another. But yeah, it's just uh, frustrating to a certain extent, but you can see from the smile on my face that I'm having a good time. So it's just yeah, it's just well, it's the process of doing science is you have to um, take data, and you have to be able to do the analysis of that data, and it's not an easy task. Not an easy task. Most astronomers spend years and years and years on one data set. They'll have like an observing run, right? That might last 2 or 3 nights, right? And uh, they have this, data set that they'll spend the next 2, 3, 4, 5 years working on, and working and working and working because of these kinds of problems, right? It's like, okay, I think I know what I have to do, right? So I'm going to go do it. I look at the results and it's like, that ain't right. That ain't right. There's something wrong. So you go back and yeah, you just do it over and over and over again. It's tedious. It's uh, uh, oftentimes mind numbing, and frustrating. No, no, because I'm having too much fun, way too much fun. So yeah, frustration would be a thing where it's like, oh man, I really don't want to be doing this. I don't want to have to do all of this, but that's not the case at all. In fact, it's the opposite of that. So and you know, the cool thing is that being a programmer as well, I'm sort of in complete control of what I'm doing. I may not exactly, you know, have everything exactly right, but at least I'm sort of in control of what the programs do. I totally understand um, um, what the programs are doing. So yeah, it's just a matter of time, and I will figure this out. That's a fact, um, because I I have an inkling that it's much better than what I'm seeing right now. Um, and in fact, in order to do what I want to do, sort of this overarching plan, which is still top secret. Um, what I'm seeing now is not acceptable in terms of photometric stuff. Um, in terms of the astrometry, yeah, it is there. It is really really nice. Subpixel um, positions. So that's sort of as good as I can expect, and so that is really really nice. But just doing astrometry, it's not quite enough. It's not quite enough. I, I want the photometric stuff too. Anyway, so looking at the binary stars got me into Gaia, and getting into Gaia sort of turns on the artsy um, part of me, and so I was looking at that sort of briefly today. I don't know if any of you saw what I was doing there. I like to I like to create art that is sort of directed by the data, and so there's an example. It's going to load, yeah. So there's an example. The so this is something like 900. Well, this is representing something like I want to say. Let's see. I think I've still got it on my Linux machine here somewhere. Where's the Gaia stuff? It's not showing up now, of course. Is that it? No, that's not it. I don't remember where the Gaia stuff is now. Oh, here it is. So this is 931 stars are represented here by the vertices of these things. So wherever you see a vertex here, any change in angle, right? That would be the position of a star in right ascension and declination, centered on sort of a randomly chosen binary star. The colors here um, were created by looking at the magnitudes of the stars and sort of converting that into a line color. So yeah, I don't know if this is interesting or not, but yeah, it's something. And then I took this exact same thing, and I ran it through uh, some things inside of GIMP, right? And I get stuff like that, right? So yeah, for what it's worth, it's kind of interesting, I suppose. But the thing that I like about it most, I guess, is that I'm using astronomical data. This so-called art is um, being directed by actual data. I'm not making any of this up. I'm not changing the numbers um, in any way. I'm just sort of adding some artistic license, right? And that's all I'm doing. So, yeah, for what it's worth, I don't know if it's interesting or not. Don't really care. It's just fun. It's just fun. I'll I'll continue, to mess around with this kind of stuff and see where it leads. I that's art for you. You just have to follow your nose, a little bit there. So, well, cool. Hey, I wanted to show off a couple of other uh, nerdy sites. Now, these two sites that I'm going to show you, I think I've shown before on other live streams, but I haven't really gone into them much lately. So I sort of wanted to again. Now, what I'm going to be showing you here in a little while is really outside of the box, right? Outside of the box, where imagination and theory just runs absolutely wild. It's like the wild west. So put on your skeptic hat for sure. Okay, be extremely skeptical, right? But also, please be um, open-minded. Consider the possibilities that what you're seeing and what you're reading might might be right or might be partly right. Nobody really knows, right? I mean, what I learned long ago, right? And here I'm going to go back to this so you don't have to keep staring at that mess. What I learned quite quite a while ago is that really it's the best story that wins. Not if it's true, not if it's anything at all. It's just the best story. Um, so let's look at some stories. Now, the site that I go to often is a site called archive.org, and you've heard me talk about that many times. Let's go over there again, and this is sort of the bleeding edge of science, and um, we're getting into physics, math, computer science, biology, finance, stats, electrical engineering, and economics, right? So any any new scientific papers that are being um, published under those topics usually lands here. Now, not all of them do, but a lot of them do. So this is sort of the bleeding edge of sort of, uh, um, you know, well, for lack of a better term, sort of normal science. Um, so, this is a great resource, right? Awesome, fantastic. And astrophysics is right up at the top. This um, this is updated every weekday at around 1 hour UTC or so. Um, and there's usually 20 or 30 new scientific papers every single day, every single weekday. Okay, so as you can see, this is archive, arxiv.org, right? Well, there's another site that's called Vikra. Okay, and Vikra, of course, is just ARXIV spelled backwards, right? So these are my kind of people, and they sort of have the same thing, but these are sort of uh, you know uh, sort of not mainstream, right? They're a little further out there in the strange universe, in the much more nerdy universe. And um, let's just look at the astrophysics one here, and you'll sort of see what where I'm. A lot of these papers are written by um, um, individuals, as opposed to you know two or three or a dozen or a couple hundred co-authors. So these are people that may not be able to get published anywhere else, right? Because peer review and maybe not very conventional thinking, maybe even not very good science, um, and so these these aren't necessarily papers that would be like rejected, but they're not. I guess they're sort of not mainstream, right? So yeah, the timeless universe, um, dense nuclear matter, the top 5 dark matter candidates, um, dwarf galaxies, big picture. You can see that this George Ranja here has a lot of papers. So this guy has been prolifically writing here, at least recently, right? Um, yeah, George Ranja has really done quite a bit. Afterglow from the Big Bang, dark matter of black holes, Herbig Haro object mystery solved. There we go. I like when mysteries are solved. And yeah, these are topics that you just don't hear much about, right? Clear trend in the mass radius relationship concerning stellar evolution. Dark matter is negative mass. Interesting. Superlight dark matter, the diameter principle of stellar evolution, neutrinos as dark matter. On the origin of asteroid 2867 Steins, I guess. Black holes, gravitational waves, Lord Kelvin's Earth, on and on and on. Just so sort of unconventional kinds of papers. Origin of the solar system. The exact formula of interplanetary distance is given. It also gives the distance formula for the satellite for centuries. This is the first one. This study pointed out that the 9 planets in the solar system orbit accuracy conforms to a formula, which we have reason to speculate that there are many planetary systems in accordance with the law in the universe. The Earth's position are universal, and alien civilization is widespread. So, yeah, a lot of these papers are written by folks, whose language, whose first language is obviously not English. So, sometimes it's sort of hard to read these, but they're available, right? So let's dive in here and just sort of see what this guy has to say about the origin of the solar system. Um, okay, yeah, some diagrams. Okay. Easy to see that the distance from the new planet nucleus to the border of the sun is halfway of the distance between the first planet to the sun. Okay. Anyway, so yeah, these folks think that they have worked something out, and pretty interesting. Here are like the observed um, distances, probably in um, astronomical units, because this is a 1 here. Um, Observed versus his calculated values, and wow, they're pretty close, right? Not bad, not bad. So kind of interesting, maybe he's um, onto something here. Maybe he's totally off. We don't know, but let's consider this. Maybe he is. Don't know. He thinks he is, right? Even Jupiter's moons, some of Jupiter's moons, he's worked that out too. Pretty cool. Pretty interesting. Uranus. Oh, okay. Pretty cool. Let's see what else we got. We don't have to go back too far. As you can see, this is going back over a month now. So on the Newtonian cosmos, there is such a hypothesis. Red color in galaxies on border of the universe indicates they're fading, like fire sparks. Huh. Okay. Wave function of the solar system. Trying to understand the universe. Yeah. Aren't we all? So anyway, just something for you to consider. Okay. Um, cheers. Now, let's go even further out. If you thought that Vixra was sort of pretty far out and weird and a little kind of, scratching your head going, oh, what is this? Right? As I said, keep the skepticism high, but also keep your mind open. Keep your mind open because, I mean, revolutions are created this way. Everything that we think we're sure of now was once an outrageous idea, completely outrageous. The Earth goes around the sun. That's ridiculous. That's absolutely ridiculous. Well, here we are. Yes, indeed. Probably the Earth does go around the sun. So any of these could be like that, right? We haven't, um, you know, there is no settled science. Anyone who says that they are sure that you know this is how it is and here's all my proof, mm, I'm going to look at that and just kind of go, okay, well, if that's what you want to think, but that's not what history says. Definitely not what history says. And to think that we're so much more advanced, I don't think so. I don't think so. Anyway, if you want to go even further out into the wild, wild west of physics and astronomy, check out Progress in Physics. Okay, ptep-online.com. Okay, Progress in Physics. Now, these guys have been doing this for a long time, right? Since like 2005. Okay, and look at some of the titles here. Cosmological cold dark matter and dark energy match um, icosahedron symmetry. The Planck vacuum physics behind the Huygens principle and the propagator theory for the Schrodinger electron. I have no idea what they're even talking about. Here's one about TRAPPIST-1, right? This is that planetary system that we're all excited about. Uh, they're using this thing that they're calling quantum celestial mechanics in order to predict um, 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 the total momentum of this system. Yeah, wild, wild, crazy stuff. Birkeland Currents in Dark Matter. That's a good read. That's a good read. Donald Scott, he thinks he has figured out an explanation for why the galaxy rotation curves are the way they are, and it has nothing to do with gravity, right? Nothing to do with gravity at all. So, global scaling of planetary atmospheres, oscillating massless neutrinos. See, this is just incredibly wild, wild stuff that really, it's try to keep your mind open to these kinds of things because somewhere hidden in here is probably the truth, right? Let's see. Gravity on the ultimate energy of cosmic rays. Quantum gravity aspects of global scaling and the seismic profile of the Earth. Huh. Anyway, check these sites out. because you know, I mean, if you want things to fly over your head and just be completely like blown away, read one of these because it's just amazing. Let's take a look at this one really quick like. So Franklin Potter predicting the angular momentum in TRAPPIST-1 and many other multiplanetary systems using quantum celestial mechanics. 3,500 exoplanets. Here, I'm going to zoom in a little bit here. Extreme examples include HD, 109 planets, and TRAPPIST-1 with 7 planets. Let's see. Angular momentum deficit. So the QCM theory dictates that not all planetary orbits out the central star are available as equilibrium orbits, but instead QCM determined equilibrium orbits exist only at specific radii. Okay. Very cool. Relation of the QCM to the solar system. Cool. Let's see. I'm not going to get into this too much, but it's sort of looking like this model also seems to match things relatively well. So, who knows? Who knows? Let's see. TRAPPIST-1. Pretty good. Looks like it's following the line there, whatever that means. Anyway, you know, these people think that they're onto something in terms of explaining whatever they're explaining, and who knows? Who knows? But as I said, you know, it's this outrageous stuff that just seems so far out and so impossible, right? That's the kind of stuff that, you know, can become our truth, right? So who knows? Who knows? All of this stuff needs to be considered for sure. Especially, you know, these people are putting a lot of work into this, right? Heart and soul. You know, even if they're totally wrong, they they definitely, you know, at least deserve a little bit of respect, right? So don't throw them out. Don't say, that doesn't match what I think it is, um, or what, you know, conventional science says. You know, if there are problems with these theories, they will be thrown out for sure, right? But if they seem to work, if they match the observations, and if they're able to predict um, things, you know, that we haven't seen yet, then yeah, maybe they're onto something. Who knows? Who knows? All right. Well, I think I'm going to finish up with an object of the day. Hope everybody's hanging with me okay. It's one of those days where we have to, you know, go past the edge of our box. You know, all of us live in these boxes, right? And some of the boxes are small and some of the boxes are big, but we all live in boxes. And it's really hard to see outside of our boxes. And these kinds of papers um, give us a glimpse of things outside of our box. And as a scientist, right? As a scientist, I think that's extremely important, even if it's totally, totally totally wrong, right? I think it's really, really important to be able to try to see outside of our little boxes. So very, very cool. All right, let's do an object of the day, end this on a little lighter note. Let's do a Messier object. Yeah, let's do a Messier object for the object of the day. Now there's 110 Messier objects. These are non-stellar objects, so they're like galaxies, um, open clusters, globular clusters, planetary nebulae, and gaseous nebulae. And so I'm going to go to random.org. Charles Messier was a French astronomer back in like the mid 18th century. He was a comet hunter. And so he was looking all over the sky for faint, fuzzy objects that moved. Well, looking all over the sky, he sort of happened upon these bright, fuzzy looking objects that didn't move. And so he wrote down this list saying, you know, don't bother with these because they're not comets, right? They don't move, don't exactly know what they are. He didn't particularly care, I don't think, what they were. They just weren't comets. So he's like, okay, um, he wrote this list down, telling astronomers, it's like, okay, ignore these, right? Well, these turn out to be extremely interesting objects. So I'm going to have random.org choose a number between 1 and 110, and we will see what Messier number, what Messier object we look at today. So drum roll, please. Oh, M110. Hey, M110 is a satellite galaxy of M31, the great Andromeda galaxy. So that's kind of neat. Let's go over to Simbad, go over to our astronomical database, and let's look at M110. Let's see what we can find out about M110 beyond what I just mentioned, which isn't much. So this is an elliptical galaxy. As you can see, it's not a spiral, right? It's just basically made of stars. I guess it's what they're calling an E5 PEC, maybe peculiar. So it's a peculiar one in some way. Can't be exactly sure why it's characterized that way. But let's see, it has celestial coordinates in the sky, position in the sky. Right ascension 0 hours 40 minutes 22 seconds, and positive 41 degrees 41 minutes 7 seconds declination. Looks like it's moving towards us at 246 kilometers per second. And it's pretty big, right? Its apparent size. So 15.11 arc seconds would be this long axis here, right? And then 9.368 arc minutes would be this axis here. So the major axis and the minor axis. Pretty bright. B and V are sort of the visible magnitudes, and then J, H, and K are leaning more towards the infrared. So it's brighter in the infrared, which sort of implies that maybe there are more red stars than blue stars. And that's sort of a characteristic of elliptical galaxies. So yeah, Patrick, you missed everything. You missed the most amazing show I've ever done. No, I'm glad you're here. Thanks for stopping in. Thanks for stopping in. Um, I hope Zoe's was fun. I I watched I watched a couple of Gilles' songs, and it looks like he was having a good time. So that's awesome. We're looking at M110 here. It's just the object of the day, randomly selected. So there's all of its other names. Most objects have multiple names, mainly corresponding to different catalogs, right? So lots of references. This is a well-studied galaxy. And this is a companion galaxy, as I said, to M31, the Great Andromeda Galaxy. Let's look and see how far away it is. It should be about as far away as Andromeda itself, theoretically. So, yeah, there's pretty good agreement, except for this last one here. That's kind of funny. But let's see. So, let's maybe exclude that last one and say what it's about like zero point 0.8 megaparsecs or so. So a parsec is 3.26 light years. And of course, that's a million of those. So times 10 to the sixth. And then let's multiply that by what, like zero point 0.8 or so. We get 2.6 million light years away. Yep, that sounds about right. And there's pretty good agreement in terms of how fast it's moving towards us, right? Somewhere around 240, 250 kilometers per second. So, moving pretty fast, pretty fast. See, there's a observation log here. Let's see. Excuse me. Let's see what this says or shows. All right, that's just some kind of infrared image of some sort of NGC 205 of uh, M110. Um, looks like it's very in the infrared, very, very much in the infrared. Not much can be seen there. Kind of interesting, I suppose. Let's see what this other one shows. Okay, so sort of the same kind of thing, just pretty low resolution. Oh, 200 micron filter. So this is looking in the far thermal infrared. In fact, that's submillimeter, right? So this is in the submillimeter wavelength range. So yeah, it's just data, right? Just plain old data. So let's see. Herschel observation log. Let's see if there's are there any other pictures? Let's see. Let's look at these. Look at these pictures. I like looking at pictures if I can find them. Taking its time here. Okay, for what it's worth. Looks like there's a spectrum and a picture. Okay. Um, oh, again, yeah, these pictures are hard to see because they're really, really, really small. So I apologize for that. But I'm seeing 158 microns. So this again is like submillimeter. wavelengths. So not quite infrared, not quite radio, not quite microwave either, submillimeter. Okay, moderately interesting. Let's see these. If there's anything interesting here. Yeah, again, it's it's uh, it's definitely data. Hopefully, it was useful to somebody. All right, cool. Let's go up and take a look at the. Let's do a quick. Because I mean, there's no way, right? There's no way that I'm going to go through 1,100 papers here. But let's just sort of look at the latest. These are usually ordered by date, right? Showing the latest ones first. So, okay, cosmic flow around local massive galaxies, the 3 pi search for planet 9. Okay, I don't know why that would be in there. Young metal-enriched cores of early dwarf galaxy and the Virgo cluster. Redshift independent distances, extragalactic database, chemistry and kinematics, Chandra survey of nearby galaxies. Chandra is a X-ray telescope up in orbit. One law to rule them all: the radial acceleration relation of galaxies. Cool. So yeah, here's something related to M31. So yeah, a lot of papers about dwarf galaxies, which um, M110 is for sure. It's also part of the local group. It looks like maybe they're looking at variable stars. Thank you, Uncle Bill. Photometry of 1 million stars in M31 and 15 other galaxies. Yeah, so they're actually seeing individual stars inside of galaxies, hopefully, probably including M110. M110 is a great object to see through a telescope too, because it's nice and bright. I encourage you all, when you look at M31, make sure to look at M32 and M110 because they're right nearby. Steady, super soft X-ray source. Most of these are related to M31, it looks like. Makes sense. All right, well, cool. Let's go up and take a look at some pictures. Pictures. No, stop that. I've got a kitty on the desk here who's causing trouble. Causing trouble. Okay, so we're going to zoom out, and of course, we're going to see eventually the great M31 as well. But this is M110, not to be ignored, right? It's a beautiful, beautiful elliptical galaxy. But you can see there's M31. Sort of, you can do a size comparison here, right? Because this is about the same distance as M31, and as you can see, it's quite a bit smaller. So this little guy here is M32, and it's also a companion dwarf galaxy to M31. So yeah, if you're ever out looking at the Andromeda Galaxy, look for these guys too, right? Because they are Messier objects, and they are, as far as I'm concerned, they stand on their own. They happen to be associated with a obviously, fantastic um, galaxy nearby us, but M110 is absolutely awesome. You know, let's zoom out a little bit more, see if there's anything else around. Oh, that's a little bit too much. There we go. So very, very cool. Very awesome. Nice galaxy. So yeah, pretty much everything else you're seeing here are foreground stars in our galaxy, right? So this and that is outside of the Milky Way galaxy, but everything else, all these stars, everything else in here is part of our galaxy, the Milky Way. So we're sort of looking through part of the Milky Way towards um, towards Andromeda, which is sitting 2.5 million light years away, something like that. Very cool. All right, M110 object of the day. Yay! All right. Well, I think the hour is up. I definitely respect all of your time. I don't like to keep you much longer than an hour. Um, Sometimes I do, sometimes I don't. This is a casual, fun get together. So there are no hard edges here. But yeah, I think it's about time. I think I've taken you sort of outside of the normal boundaries, and then pulled you back into to more normal stuff. So yeah, I like doing that from time to time. So yeah, in your 4-inch, Uncle Bill, you definitely you will be able to see those, but you got to be out dark. You got to be out really, really dark, and use um, um, averted vision, right? That's where you look off to the side, but you concentrate your attention on uh, where you think the galaxy is, and it might pop. At In a dark site, you should be able to see M110 for sure. You can definitely see 32 for sure, for sure. It's small and very, very bright. M110, as you could see, was bigger and more spread out. But yeah, you should be able to see it with a 4-inch. Definitely, definitely. It's not going to be easy. That's sort of right on the edge. But yeah, you should be able to see it, especially in a dark site. Look off to the side, as I said, and it should probably pop. It should probably pop. Sometimes, sort of moving the telescope around a little bit, seeing things move. Sometimes that helps too. So try that. But yeah, you should be able to see it um, with a 4-inch. Yeah, yeah. All right, I'm going to get out of here for now. I think, yeah, the mothership is definitely calling. So I'm going to get out of here for today. Glad you all could stop in to this, gathering of friends on sort of a virtual porch where we, grab our beverage and or consumable of choice, and sit around and just share a passion, right? Share the passion. That's astronomy, and Yeah, you know, it's the study of everything. There is never a lack of things to talk about for sure, and there's always something new, always, 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 always. So, all right, take care, everybody. I will see you on the spin. On the spin. Don't get dizzy. Hold on to your hats. It's a smooth ride. It's a smooth ride. You've done it many, many times. So no, no worries about spinning off or anything like that. You know, we're pretty well planted here. So yeah, I will see you again in a little less than 23 hours from now. All right, have a great evening. Have a great day, and I will see you tomorrow.